electricity and magnetism, putting them on the path to a unified theory of the world. So when James Clerk Maxwell went to Cambridge University, light was almost inevitably one of his main areas of study. Maxwell has come down to us as an odd character. Everything interested him. He pondered the maths of why cats always fall on their feet, and why paper fell in particular patterns. Could there be some kind of law behind them that would enable him to draw up universal rules for how the world worked? He even tried his hand at poetry, though, as history will probably judge, with much less success. When a telegraph cable under the Atlantic failed to work, Maxwell wrote an ode.
Under the sea, no little signals are coming to me. Under the sea, something has surely gone wrong. And it's broke. What is the cause of it does not transpire, but something has broken the telegraph wire.
Yet behind the amateur versifier was a brilliant analytical mind, which was to fuse two traditions which until now had never seen eye to eye: maths and engineering. It would be an explosive combination. The clash of these two traditions would enable Maxwell to use maths as a tool in a way nobody had ever attempted before. It would help him explore light in a totally new way. Yet surprisingly, the biggest revelation about light would come from another problem that fascinated Victorian society: the relation between electricity and magnetism. In 1831, Michael Faraday had demonstrated that if you wave a magnet near a coil of copper wire, it would produce an electric current. What nobody could explain was why. Maxwell set about looking for a mathematical explanation. It seemed impossible. He had to invent a new mathematical language. And what this gave him, after a huge amount of work, were 4 stunning equations that showed for the first time the precise relationship between electricity and magnetism. That in itself would have been an extraordinary achievement. But there was more, because hidden in them was something else: the truth about light. The particular excitement about this set of equations is that they start off by describing the phenomena, not of light, but of electricity and magnetism. If you represent the way in which electric and magnetic forces interact with these 4 equations, you start to see that light, electricity, and magnetism have something to do with each other. But then there's more. This number, which appears in the equations, describes the speed with which waves travel in electromagnetic space, and it turns out that the speed with which these waves move is exactly the same as the speed of light. There could only be one explanation. Light, electricity, and magnetism must be the same kind of thing. Light is an electromagnetic wave. It was one of the biggest insights into how the world works in the history of science. Most of his contemporaries found it impossible to grasp. For Maxwell, the world now fitted together beautifully. If light is an electromagnetic wave, then the different colors of the spectrum correspond to waves vibrating at different frequencies. There's red at one end. This is light that's vibrating pretty slowly. And then as the speed of vibration increases, we see the colors from red to orange, all the way up to blue and violet. Violet light vibrating extremely fast. Other mysteries also fell into place, like the apparent presence of light, even when it can't be seen. Beyond the visible spectrum, there's something very spooky indeed. There's invisible